Okay, so Assalamu alaikum wa rahmatullahi wa barakatuh once again. Today we are going to start session number 7, which is related to design of an isolated or design of isolated foundations, let's say. Now in the previous lecture, Ms. Mazoon has taken with you a session which was related to the fundamentals of foundation design. Okay, in which she has introduced the different types of foundations, and then she has given you some brief about when to use each one of them. Okay, today we are going to go to a more deeper perspective of foundation design, and then we'll see how to properly design an isolated foundation. Okay. Now first, do you have any question regarding last class or the class before, which is load transfer? In load transfer, I have given you a problem to try. Have you tried? Okay, no problem. So if you have any question regarding these previous classes, then you can ask them in the post that they have kept for question and answer. Now, are you able to see the screen? Are you able to see the screen?
Yes.
Okay. So once again, today's topic about the design of isolated foundations. Now, isolated foundation, as Ms. Mazoon told you, is going to be having different forms. It can be an isolated, it can be isolated as well. Sometimes we call them pad foundation, which can be either isolated or a combined foundation. Okay. Now for isolated itself, we have two categories. We have one which is called eccentric foundation, or concentric isolated foundation, and then we have eccentric isolated foundation. And we are going to learn what are the differences between these two and how to design each one of them, inshallah. Okay. First, there are certain general guidelines that we need to understand before entering to the design of isolated foundations, and some of these guidelines have been already discussed to you roughly by Ms. Mazoon. Now it says for you the maximum bending moment is occurring at the face of the column in pad foundation. Okay. Once again, general design perspective, when we design any foundation, the maximum bending moment is happening at the face of the column. Is it clear what is the meaning of this? Is it clear? What is the meaning of that the bending moment is maximum at the face of the support, or the face of the column? Now let us draw an isolated foundation. I'm assuming that I have an isolated foundation. Now can you tell me what are the loads coming on this isolated foundation? What are the things affecting this isolated foundation? One is a load from the top, mainly. Just 1 second. Okay. So loads from the top. And then we have the soil capacity, whatever we call it, soil capacity. Okay. Now, what will happen? We have a concentration of the loading from the top, and we have a concentration of loading which is happening from the bottom. Now you can see in this location, this particular element will not bend. Okay, or this particular location will not bend. Why? Because we have a lot of concentration in terms of the load coming from the top, and there is the loading from the bottom. Okay, it is like I'm having a paper, okay, and I'm keeping, for example, a pen in a paper. Okay, once again, I'm holding a paper, I'm keeping a pen on the paper, and I'm trying to push it from the bottom. Okay, you will see that this part is going to bend upwards. This part is going to be bending upwards, but the point where the pen is there, or the concentration of the top load, it will not bend. Do you agree with me? Once again, just imagine that I'm having a paper, and for example, I'm having a bottle of water. Let's say I'm having a paper, and then I'm having a bottle of water, and then I kept the bottle of water at the top of the paper. Now I'm trying to apply a load from the bottom. I'm trying to, let's say, bend my foundation from the bottom. So you will see that the foundation will be, or my paper is going to be elevated or bend up, except for the position of the water bottle, because it's getting me down. Are we clear about that? Is it clear that the location of the loading or the location of the column will not bend? Are we fine? Or do I need to explain further?
Yes, Mr. Clear.
Okay. Now, can you tell me how would you draw the bending moment here for this particular element? Now, if you say this is my foundation, because we said drawing the free body diagram, or drawing whatever we called it as uh, the free body diagram, okay, is very important. Okay. Now, if you see, what do we have? This is my element, which is a foundation, and then we have here different loads, which are representing the capacity of the soil. You will see that your soil is going to try to push the element, is going to resist the element. Okay, so this is whatever we call it as soil, let's say, capacity. Okay, and then you will see that you have a loading here coming from the column. Now, if we want to try to draw with the bending moment, then it's easier for me. It's easier for me to shift this system to a system that I understand, which is going to be this one. Now, can you see that it's easier now for you to analyze, because this is a system that you used to know, or you used to deal with? Okay. Now, if you see, it is like we are having a support, which is here in the gray color, and then we have loading coming from the top, which is representing the blue color. Now you can see that these two, scenario number 1 and scenario number 2, are only opposite to each other. So the bending moment diagram should be the same. Okay, the only thing that instead of going up, it will go down, for example. So now you can see the bending moment for this scenario. If you see, this is This is used to be acting as a continuous support because it's continuous from both sides. So my bending moment used to be like this. Do you agree? Now, of course, here it goes to zero because there is no other thing. Okay, it goes to zero because there is nothing else. It's the end of the foundation. Did we solve something like this? Did we draw bending moment something similar? Are you with me? Are you able to hear me?
Yes.
Yes, with you,
Okay.
Mr.
Okay. Now, if you see, since we have rotated from scenario number 1 and scenario number 2, we will see for scenario number 2, the bending moment is going to be the opposite, which is going to be in this sense. That this is going to be my bending moment of my foundation. Okay. Once again, this is a scenario that we know, and this is a scenario of the foundation. Now we have drawn the bending moment for a scenario that we know, and we just flipped it, which is representing the foundation. Okay. So now what we want to say that the bending moment now for this particular foundation is going to be of this shape. Now we said that this particular position where it is for the position of the column, we said that it will not bend, right? We said it's not going to bend. So now if I want to find the maximum bending moment, okay, if I want to find the maximum bending moment, then the maximum bending moment will be here and here. Okay, it is going to be here and here. Why? Because we said the center portion where there is the column, it will not bend. And once again, you can try it with your bottle of water or the pen. The position or location of your element is not going to be bent up. Okay, the other areas are going to be bent up. Okay, so now what we understood that the maximum bending moment will be occurring here and here. Okay, now where are these two locations? These locations are representing whatever we have mentioned in our guidelines by saying that the bending moment is maximum at the face of the column. And once again, if you go and see here, you will see that this point is representing the face of the column, and this point is representing the face of the column. Okay. So once again, when we design an isolated foundation, we need to calculate the bending moment at the face of the column. Why? Because at the position of the column, the bending is not going to be happening in reality. Your column will never bend in that location. Okay. Are we clear about this thing? Are we clear about it?
Excuse me, Mr.
Yes.
You mentioned in the beginning you have to load from the top, from the column, and the bottom to the from the soil. What about the soil? Will be not
What about
load
which soil you mean?
capacity of the soil.
Yeah, it is going to be a load. That's the load which is bending you.
We so we don't bend to the will push to the up.
Yeah, the soil is due to the loading which is happening because of the column. Now, if you say if I have a paper and I have a pen and I'm trying to push my pen down, you will see that the paper is going to be going up from the side. Can you relate? Can you try with a paper?
Yeah, just
Okay, you
clear.
will see that, yeah, you can see that the paper is going to be bending up because of the load of the column. Okay, are we clear? Is it
Yes.
fine now?
Yeah.
Okay, so once again, we learned that we need to calculate the maximum bending moment at the face of the column. Now, of course, if you see here, there are two positions when it comes to a foundation. Okay, when it comes to foundation, because we have two directions. Now, if we have, for example, if we have a foundation which is, like, let's say 3 meters, and then this is 3 meters, and then I have a column. The column is, let's say, 200, or let's say 400 into 400, or 0.4 meter. Now you can see in this scenario, this distance from here, okay, is equal to, this is like in one direction. Now let us talk that this is the first direction. Okay, in this direction, my distance is equal to how much? How much is this going to be? Can you help me here? How much is this distance? Distance x, for example. How much is it? You will see that distance x is equal to 3 meters minus 0.4 divided by 2. So the whole thing, 3 meters minus 0.4, which is the column, divided by 2. Okay, which will give you 1.4, or you can calculate it as well. X is equal to the distance from here, from the beginning of the foundation till half of the column, is going to be 1.5 meter. So 1.5 meter minus, this is 1.3. Okay, 1.5 minus the half of the column here. So that's going to give you 0.2, which is 1.3. So both methods are fine. You can calculate it using any method. Now you can see that this distance when it comes to x is equal to 1.3. Now what about the other direction? In case of, for example, y. Okay, in case of y, you will see in this scenario that it's the same once again as 1.3, right? As 1.3. Okay. Now, if you see here, now this is acting. If we take this particular point, we have a distance of L, and we have a loading of W, and this bending moment, this maximum bending moment, is now acting like a cantilever. Okay, now is acting like a cantilever. How is it going to go? It acts like this. So this is my column. Column is acting as fixed support. It will not move from its position. And then we have a loading. So it acts in this way. Okay. This distance from here to here is considered as L. This distance, this loading, is considered as W. And you can see that the maximum bending moment at this point and at this point is going to be equal mW square over 2, which is the bending moment for a cantilever case. Okay. So now we learned that the bending moment is going to be WL square in case of a cantilever, which is the case of an isolated foundation. Okay, which is the case of an isolated foundation. In case of concentric loading. Okay, in case of concentric loading. Okay. Now you see that the whole moment value is depending on the value of L. It means that if your L value is different from side number 1 to side number 2, then you will be having two moments, not one moment. Do you agree with me? Like, for example, if we have this scenario, this is my foundation, and then this is my column. Now this foundation, let's say it's 2 meter here, and then 0.8 meter here. Okay, and I told you the column is 0.2 into 0.4. Now, can you tell me how much is the distance in each and every scenario? Now, you will see that this distance from here to here, okay, which will be called as x. My x is going to be as, let's say, 2 meters minus, of course, this dimension is 0.4. So 2 minus 0.4 divided by 2 portions. This will give you 0.8 meters. So my x value is 0.8 meters. Now, how about the other direction, which is your y? Now you can see your y value is equal to 0.8, which is the whole distance, minus this distance, which is 0.2, because we said the column is 0.2 into 0.4, minus 0.2 divided by 2 portions. So this will give you as 0.3 meters. Now you can see that we have two dimensions, or two spans, or two lengths. One is x and one is y. Now remember, when you draw the bending moment for this scenario, you will be having two sides. So there will be one bending moment like this for the 2 meter side, and you will be having another bending moment in the other side, which is like this. Okay, and you can see now that this particular bending moment corresponds to here, and this bending moment corresponds to here. So we need to know this distance, which is in this case 0.8, and here it's 0.8. We already know the distance. If we know the loading, then we can calculate the bending moment. The same scenario here. We got the first point, and then we are going to get the second point. And you can see that this distance from here to here is only 0.3 meters. Okay. So now what will happen? Because of the span here being 0.8, we are going to have 1 m. Because the span here is being 0.3, we are going to have another m. Are we clear about this? If the distance is almost the same, then you can take them as 1 m. If the distance is the same, like the case that we have talked about here, then you will end up having m1 equals to m2. So you will take only one moment to be designed for. And then you will say that reinforcement is going to be supplied in both directions, because my moment of 1, or my moment of x direction, is the same as the moment of y direction. Are we okay about this? Are we fine? Are we fine about the bending moment?
Yes,
Okay.
Mr.
Okay. Now related to the concentric and eccentric. Okay, related to concentric, concentric and eccentric. What is the meaning of concentric and eccentric? Anybody? Concentric and eccentric. Any person? It's fine to try. Okay. Now when I say concentric, now we have this is representing concentric at the axis. One is the center, y, the other is not. Okay. Good. Good. Okay. So you can see now here we have two elements. Okay. We have element number 1 and we have element number 2. Element number 1 is representing a column. Element number 2 is representing the foundation. Now you can see, if we're taking it for scenario number 1, let us have 2 scenarios. Scenario number 1, and this is my foundation. Now you can see that the center of the foundation is located somewhere here. Now if your center of the foundation is acting with the same center of the column, if the center of the foundation is acting with the same center of the foundation, we call this as concentric. Okay, concentric. Now, if the loading of the column is not in the same line of the center of the foundation, then we say that it's eccentric. Where you can see that this is the center of the foundation, and now this is your center of the column. Okay, now you can see for scenario number 1, you can see that this element is to be designed for whatever we call it as axial stresses. Okay, axial stresses, which is going to be taken into account axial force divided by the area of the foundation. Okay, which is P over A, or in certain books and references we call it N over A. Both of them are fine. Okay, so it is N over A or stress over A. I mean P over A or N over A. Both of them are the same. Okay. Now you can see why we have said N over A, because actually there is one loading coming from the top, which is called N or P. Now for the second scenario, what will happen? We have the same N or the same P. Let's say, let us call it P. P as an axial force. But in the same scenario, what do we have now? In the same scenario, what do we have? We have a bending moment, and this bending moment is caused because of the eccentricity, which is here. Do you remember whatever we call it, the couples? Where now we are going to have one moment which is equal to P into E. Okay. So now we don't have only a moment, we don't have only a bending or an axial force, but as well we have a moment which is caused by the fact that my loading is not at the center. My loading is at a certain side. Now to represent this very clear, or to make it a bit clear for you, now imagine you have the tissue box. Okay, imagine that you have the tissue box. Now for the tissue box, if you are putting it at one end, you are supporting it, for example, by a table, and then from the other end you are supporting it by the table, and then you are pressing exactly at the center of the tissue box, you will see that the tissue box is going to try to go down only. Okay, because of the compression or because of the axial force happening. Now, if you are not pressing at the center of the tissue box, you are pressing at one side, you are trying to go near to the right end or the left end, you will see that not only it will try to go down, but it will try to go up as well. It will try to bend with you. You will see it from the other side, it's bending going up. Do you agree? Okay. So now what will happen? You will see that this portion of the foundation will try to go down because of the bending that is happening. Okay, and this portion is going to go down. or to go up. Okay. So this portion is going, if you continue the rotation of the moment, this portion is going to go down, this portion is going to go up. Okay, which is represented by here that this is going down and this is going up. Are we clear about it? Are we clear? So if we are having it to be eccentric, now we will not have only P over A. P over A is there because we have an axial load, but as well we have M. So in that scenario we have something called M over Z, where the first one is called normal stress and the second one is called to be your shear, is called to be your flexural or bending stress. Okay. So wherever there is a direct, wherever there are you able to see the screen now?
Yes, Mister.
Okay. So now once again we need to understand our foundation. Okay, whether there is only a loading, and in that scenario we are going to design it as a concentric, where we are taking only the stresses which are normal stresses, which are P over A, like the example of the tissue, or the second scenario where it's eccentric. You will see that it's not only to be designed for the loading, but it's also designed to resist the bending which will be happening. Are you able to relate with the tissue box example? Once again, if the loading is acting at the center, we need to deal with the compression which is happening. So my foundation of my element is designed for that particular loading. Now, if my loading is not at the center, my loading is at one side, you will see it will not only be compressed, but it will bend in one side. So now when I'm going to design it, I need to design it for both. For the loading, which is P over A, and for the bending as well, which is M over Z. Are we clear? Are we
Mister,
fine?
questions.
Yes.
If it's there is a 2P affected to the foundations, it
What do you
can
mean
be
by two? What do you mean by 2B?
it can be combined between the construct and
Combined
extract.
foundation. Combined
Yes.
foundation. Yeah, we are going to see combined foundation in the other classes. Don't worry about it.
Okay.
Do not rush things. Okay. And this is going to be my bending moment or my pressure diagram to be accurate. This is going to be my pressure diagram for in case of eccentric. Yes, Martin, tell me, what is not the thing? Which thing is not clear? And my pressure diagram is going to be unified. We don't have a position which is having more pressure than the other position. While here, because of the moment, the pressure here is higher. Okay, once again, for the concentric, we don't have a position which is higher, having a higher pressure than the other position. Now, because of the fact the load in the second scenario, because of the fact the load is not at the center, you will see that we have a pressure in certain location more than the other location. Okay, which is represented by the pressure diagram. The location where the bending is occurring, or which bending is happening more, it tends to bend in which direction is going to have more pressure. Matas, on which part exactly? Which part to be explained? Finish, mister. Which finish? Okay. So once again, we have concentric and we have eccentric. Concentric means that the loading of the column is located at the same center of the foundation, which will eliminate any additional moment. Okay, we will not have any moment because it's at the center. So my element should be designed only to resist that particular loading. Now, in case of the eccentric, the center of the loading of the column is not at the same location of the center of the foundation, which will cause some eccentricity with a value of E. That value of E will cause my element to bend. And I have given you an example of the tissue box. We said if you are pushing at the center of the tissue box, you will see that it will never bend in any direction. It will try to go down. It will try to compress. If you are trying to apply your loading in one of the directions, you will see that it will try to compress, and then as well the other end of the tissue box is going to go up. Okay. So it means that I need to design for two things. I need to design my element to resist the compression which is happening and to resist the bending as well. Okay, so that's the main difference when it comes to concentric and eccentric. Okay, it will be a bit more clearer whenever we are going to start solving issues or start solving problems. Okay, now this is only for one slide, and we have learned that we need to calculate the bending moment into different sides. But the most important thing for us is to understand that the bending moment is to be calculated at the center or to be calculated at the face of the column. Okay, to be calculated at the face of the column. Now the other two things that we need to take into account as well is whatever we call it one-way shear, two-way shear. Okay, one-way shear and two-way shear. Now as it is mentioned in the name, one-way shear is going to be happening in one direction. Two-way shear is going to be happening in two directions. Okay. And just to illustrate these, what we are going to do, we are going to have one-way shear. And then we are going to have two-way shear. Now, another name for one-way shear is called to be transverse. Another name which is widely known for two-way shear is bunching shear. Okay, so we have bunching and we have transverse, or we have one-way shear and bunching. Another name here as well, sometimes they call it as a beam shear. Okay, because it takes one line. Anyhow, any of the names are fine, but you should know bunching because it's more widely used for two-way shear. Anyhow, what we want to say that this is my column now. This is my foundation. Okay. And then we have a certain loading going here. And we said, as we said, we have the pressure from the soil going up. Now you will see, actually the loading of the column will not only be in this location. Okay. The loading of the column will start distributing in a 45-degree manner. Okay. So whatever loading is here is going to be distributed in this area mainly. Okay. So the code says to you that if you are trying to cut, if I'm trying to cut my element, okay, if I'm trying to cut my element, it is almost impossible to cut in this location. Okay. It is very hard for the foundation to be cut from that location because we have a column. When I say cutting means I'm trying to go up. And you can see in that location which I have drawn with a box, it is very hard for me to go up because of the location of the column. The soil will not try to cut your column. Okay. So the code says for you, the easy part to be cut is this portion from here to here and from here to here. These are very easy parts to be cut. Okay, these are two easy parts or the easy parts to be cut. Now how to find that or how to calculate that, the code says for you after different analysis or different verification, they say it for you. Shear force will start cutting after a distance of d. So the code says for you that this distance is equal to d. This distance from here to here from the face of the column is called d. So the area where I'm going to be affected by shear, there is a possibility of having shear, is going to be this area. Okay. And how to get that? We need to calculate first the value of d, and after getting the value of d, we will know how much is this particular length and how much is this particular length. And accordingly, we are going to design for it. Okay. That's in case of one way. Once again, the whole concept is that we have two loadings. One is the column loading, another one is the soil loading coming from the bottom. Okay. Soil loading is trying to resist, it's trying to keep the soil in its position, so it's trying to apply an upward force, okay, to allow the soil to stay in its position. The column is trying to push down. Okay. Now what will happen at the location of the column, and the part closer to it, you will see that it's very hard for you to cut. Okay, it is very hard for you to cut. It is something similar to having a paper, and then you are trying to apply a downward force. Whenever you try to cut, you will see that it's impossible for you to cut exactly at the side of the element. Like for example, if I have bottle and I'm trying to push my bottle at the paper or to the paper, you will see that it is hard for you to cut exactly at the side of the water bottle. You will see that always you will take a bit more. Okay, because once again the effect of the loading is not only at the position of the column, but it extended, or it's getting extended to a certain extra location, and that extra location is verified by the code by the value of d. Okay, now the same thing goes for two-way shear. Now in two-way shear, what will happen? This is in terms of let us say first. This is in terms of section. In terms of plan. Okay. This is my plan, and this is going to be my foundation. We said plan. Let's say plan 1. Okay. We said we need to take a distance of d. from the face of the column. There is D. And we said that this area is the area which is easily cut. This area or this area. Now of course you need to take the if the foundation is not symmetrical, as we have illustrated for the bending moment, you have two lengths, and then of course you will be taking the higher length of the two. So for example, if I have this is to be my L1 and this is to be my L2, if both of them are the same, then it's fine. If L1 is bigger than L2, then I'll take L1. Okay, the same thing. Whenever I increase the length, the bending moment will increase. The same scenario, if I increase my L, my shear will increase. Okay, so from whatever lengths are given, you need to take the highest one. Now this is in one direction. You can see that these two areas are happening in one direction. So you need to take either the left or right, depending on which one is higher. Now the same scenario can be for the other direction. Okay. So if this is my foundation, and this is my column, it can happen from the other direction as well. So this can be my D, and this can be my D, where this can be the affected area, or this can be the affected area. Okay. So now what we need to do in case of one-way shear, it happens either in the direction of short direction of the foundation, or it happens at the longer direction of the foundation. Okay, and we need to check for both scenarios which one is having a higher length. Once again, why we are taking higher length? Higher length will give you the higher shear force. The higher shear force is going to be checked against the concrete strength. If the concrete is already strong enough to take your highest shear, then of course it will take the other lower shears, and we are going to see that in the calculation. Now, when it comes to two-way bunching or two-way shear, okay, it is not going to be happening at X or Y, okay, or long and short. If you remember, in one-way shear, we are going to have either short or long. It happens in one side only, or one direction only. Okay, so either X or Y. Now for two-way slab or two-way shear, it happens in both. It happens in both, that they will be cut in the same time. So the effect that this is my column, okay, you will see that this portion, this portion, and this portion is affected. Now, just imagine one thing. Now, if you have a paper, if you are having a paper, and you are trying to bring your pen, and you are trying to push the pen very strongly in the paper, what will happen? Once again, I have a pen and I have a paper. I'm holding the paper. I'm trying to press the pen on the paper. Okay. What will happen after pressing a lot? Once again, this is my paper. This is the location of the pen. I'm trying to press the pen heavily. Okay, and I'm trying to apply. What will happen? What will happen if I kept pushing the pen on the paper? Huh?
The sides will go up.
Yeah, you will see that the pen will cut the paper, right? The pen will cut the paper. Do you agree?
Yes, mister. Agree.
Okay. Now, if you see, if this is my tip of the, if this is the head of the pen, now you will see always when you try to cut, it will not only take the tip of the, or the area of the tip of pen only. You will see that whenever you are trying to cut, you will see that a bigger area is taken. Right? You will see that whenever you try to cut, it's not only the area of the pen. You will see that slightly bigger area is taken. Okay, and you can try it yourself. Whenever you are trying to cut a paper with a pen, you will see that it's not only the area of the pen. You will see that you are going to take little bit extra of an area. Okay. Now, in this scenario, what the code says for you, if the column is so strong and it's trying to bunch, it's trying to cut your foundation, okay, something called bunching shear needs to be checked. Okay, needs to be checked, which is going to be having a distance of 1.5D. Okay, so now instead of having 1D, now we are going to have 1.5D according to the code. Okay, now what happens? Now you will see this portion, whatever portion I have drawn now, this portion is going to go down the pen, and that area is going to go down. The other areas, what will happen to it? The other areas are going to go up. Okay, they are going to go up because the pen is pushing down very strongly. You will see that your paper will go up. Okay, the whole remaining part of the paper. Okay, now that effect of the pen is going down and the paper is going up or staying in its position is called shear. Okay, and since the whole part is going up or staying in its position, okay, it causes you something called punching shear. Okay, and for punching shear, the code says for you, punching shear will be affected. The part now which will go up in this particular plan is going to be this part. So it's like you imagine the position of the column is representing the pen. 1.5D from each side is representing the extra part which will be taken with the pen down. The remaining part should go up or remain its position. Okay, so this is what is the concept behind checking for one-way and two-way shear. Okay, so once again, in one-way shear, it represents the foundation going up. The foundation is trying to cut the column. Bunching is representing the opposite, where the column is trying to punch or cut my foundation. Now, for me to be safe, I need to check for both scenarios, that these are maintained. Okay, both scenarios are maintained. Okay, now these are the things that you need to do, or you need to know, that bending moment is to be calculated at the face of the column. One-way shear, as we said, after D from face of the column, and then two-way shear. It will happen after 1.5D from face of column. Okay, so once again, from the side of the column, I need to take a distance of D. Okay, a distance of D in case of one-way shear, and a distance of 1.5D in case of a two-way shear. Okay, so these are the things that you need to know and deal with. Okay, while solving the foundations. So these are related to some basics of foundation. Some figures here are representing whatever I have told you. Okay, so you can see here, you can see in this location that this portion is going to be bending up. This portion is going to be bending up. Okay, this location is not going to be bent. That's why when we calculate, the bending moment is acting at the face of the column. Okay, so that's why you can see that this is the location, or this is the axis which has been taken for the bending moment. Okay, now you can see that here they have represented for you one time L, another time they have represented for you M. Yeah, something similar like whatever has been illustrated by Safana. You can see that the column will not, if the column is happening, but this is a flat slab. Okay, flat slab is an opposite thing of a foundation. Okay, flat slab is an opposite side of a foundation, or a opposite, let's say, arrangement of a foundation, where you have slab at the top and then the column. In a foundation, you have the column, and then at the top, the slab or foundation. Okay, but once again, bunching shear is the same. Okay, now you can see at the location of the column, it's not only cutting the column side, it's not taking the column area only, it extends that more. And to understand it, as I told you, if you try to bring your paper and your pen, you will understand it clearly. Okay, you will see that whenever you are cutting, the pen will not only take the area of the pen will try to take little bit more of an area. Okay, you can try it and then see. Returning back to our presentation, you can see that we have said two values of M should be calculated for both directions. Okay, for both directions. If the foundation is somehow symmetrical, then your M1 and M2 are the same. If the foundation is not symmetrical, then you need to have M1 and M2 and design for both of them, like we are designing for two-way slabs. Okay. Now here for one-way shear, you can see that one-way shear will be happening after a distance of D, and this is due to the 45-degree what you call load distribution. Okay, you can see here represented in 3D. Okay, so shear is going to be happening. The part which will go up is only going to be this part. Why? Because this part is still having the strength of the column. It's very hard for me to cut it and take it up. Okay, so the part which will go up is going to be this part or this part. Okay, that's in case of a one-way shear, which is at the distance of D. And then we have bunching shear, which is at the distance of 1.5D. The triangle here is appearing more. Why we have taken 1.5D? Because there is the effect of two direction, not only one direction. Okay. Once again, it's very hard for me to uplift the column in this direction, or to uplift the foundation in this direction. Why? Because of the presence of the high load of the column. So the part which will go up is going to be this part. Let's say this part, whatever we have it as 1.5D. This is the part where only I can lift now. Okay. Are we clear? Are we clear about the concept of one-way shear and two-way shear bending moment for the foundation? Okay. Certain other things that you need to know. Minimum grade of concrete to be used for a foundation is C35. So I cannot use something lesser than C35. Okay. The minimum grade, which is suitable for very severe condition. Normally, the foundation is to be designed for very severe condition because the foundation is interacting with the soil. Okay, interacting with the soil, so it needs to be designed for very severe very severe condition, and the minimum grade to be used is C35. Now we have the cover here. If you remember, we used to calculate the cover based on the water and fire. Now, according to the code has kept it direct for you in terms of foundation. It says for you that you have two scenarios. You have the scenario with BCC layer or without BCC layer. Okay, with blinding layer or without it. Now, normally here in Oman, before building our foundation, we normally do a BCC layer. Okay, so if you are having a BCC layer, it says for you that the minimum is going to be 40 to 50. Okay, so the minimum is 40. In Oman, we use 50 mm. Okay, we use normally 50 mm cover for the foundation. Now, if you don't have a BCC, if you don't want to use BCC, then your cover is going to be 75 mm. Okay, your cover is going to be 75 mm. Now, here in Oman, we don't go without BCC. Normally, we are only using BCC, and then the cover is normally adopted to be 50, but the minimum according to the code is 40. So once again, you should know that if we are having a BCC, then how much is the possible cover? If we are going without BCC, then how much is the possible cover? Now, do you think that we need to design our foundation for fire? Do you think fire will be attacking the foundation if it's inside the soil? No. Okay, so it should be only, when I talk about durability, it should be only designed for water. I don't need to check for fire, because it's not logical for me to say that fire will be eating my foundation, which is already at 1.5 or 1.8 meter of deep in the soil. Do you agree?
Yes, Mr. Agree.
Okay. Now coming to the part where we are talking about the loading. Now, how many loadings do you think are coming on a foundation? If we talk about the foundation, how many loadings are there? How many loadings are coming on a foundation? Now, you remember when we have talked about the beams, we said the loads coming are from the slabs and the self-weight and maybe the wall, if there is any wall. Now, what about the loading coming on a foundation? How many are these? Three, 4, 5, 6. Okay, we'll see them. We'll see. Now, this is my This is my column. This is my foundation, and this is whatever we call it, NGL or natural ground level. Okay. Now the first load is whatever we call it, self-weight of foundation. Do you agree that the first one is self-weight of foundation? Self-weight of the foundation. Okay. Second one. Is loading from the top. Loading from the top. That's the second one. Third one. Now, of course, there will be soil here, right? There will be soil at the top of the foundation here. Okay, so this is number 3. That's a backfill. Number 4. Number 4. And some of you have said number 4. Number 4 is going to be something called surcharge. What is the meaning of surcharge? What is the meaning of surcharge? Those who have studied geo.
Mr. Alud, that can be fixed into the natural ground level, and it will be compact the soil into the.
Okay, so it's an extra layer of soil. Okay, it's an extra layer of soil, which will differentiate normally between the level of NGL and then, for example, finishing ground level. Okay, so we have our finishing ground level here, for example. So now we have 4 possible loads. Okay, 4 possible loads, which are self-weight of the foundation, loading from the top, backfill. Surcharge are normally rarely happening, but normally there will be 3. One is the self-weight, second is the loading from the columns or from the top, third one is the backfill. Okay, so we are going to learn how to deal with these loadings. Okay, are we clear about them? Are we clear about them? Are we okay about the loadings? Any question regarding them? Okay. So now what do we have? Let me just erase this. Can you please just mute yourself because I'm hearing a lot of noise? Okay, thank you very much. Okay, so you can see now, we said the total axial load is loading coming from the column plus self-weight of the foundation plus the weight of the backfill plus the weight of any surcharge. Okay, so there are 4 loads normally accumulating whatever we call it P value. Okay, so P value is consisting of these 4. Okay, not always all of them are going to be present. Anyhow, whatever things are available. Now, of course, self-weight will be there. Loading from the top will be there. Weight of the backfill always will be there. Okay, but sometimes the surcharge is available, sometimes it's not available. Okay. Now further, we are going to learn basic concepts about pressure on the soil. Okay. Now, what is the difference between stress and pressure? Anybody? What is the difference between stress and pressure? Any person? Now both stress and pressure are having an equation of force over area. Pressure is force over area, stress is force over area. What is the difference between them? Now when I say, just imagine that I'm a person. Now when I say that the pressure will be coming from inside or outside? The pressure is coming from inside you or outside you? Yeah. The pressure will be coming from your inside or from your outside? The pressure. Once again, the pressure will be happening from outside or from inside? Okay, so pressure is going to be from outside. I'm going to have pressure from outside. For example, the college is causing you a lot of pressure now because of the examination. So there is a source of pressure, which is the university or the college, right? Now, because of that, what will happen? Because of that, stress will be developed from inside. You will be stressed, right? So pressure is external, stress is internal. Okay, so when I talk about pressure and stress, to differentiate between them, pressure is external while stress is internal. Okay, once again, For example, you are having a lot of examination, a lot of things from the college in these days. There is a source of pressure. The college or the university is applying some pressure on you. So you can see that the pressure is external. It's applied from outside. Now, due to that pressure, I feel stressed. From inside, I'm feeling stressed. So stress is going to be coming from inside. Pressure is going to be coming from outside. In conclusion, pressure is external. Stress is internal. Okay. So that's why we said pressure on soil. Because the loading is going to cause a pressure first. Okay. The loading which is coming from the top is going to cause pressure on the soil. Okay. Now let us see these two examples. We have pressure on the soil, which is force over area. Okay, that's the pressure. That's the equation of the pressure. And we have something called SPC, which is safe bearing capacity. Okay. As Ms. Mazoon said for you, there are 3 types of bearing capacities. If you have studied geo, you have ultimate bearing capacity, you have safe bearing capacity, and then the last one is going to be your net bearing capacity. So safe, net, and then you have ultimate bearing capacity. Okay. Now what I need to understand, this safe bearing capacity is the maximum capacity which can be taken by the soil. This is the maximum stress the soil can take. Okay. This is the maximum stress that can be taken from the soil. Okay. Now let us assume in this scenario that my SPC is 150 kilonewton per meter square. Okay. So the soil, what I'm saying for you, that we have a soil here. This soil is going to take up to 150 kilonewton per meter square. Now I need to check the loading which is coming from the top. Okay. The loading which is coming from the top is going to be how much, causing you how much pressure. Okay. So now you can see because of this particular loading, there will be a certain pressure. Because of this particular loading, there will be a certain pressure. Okay. Now I need to check. Now, will the pressure is more than the stress that can be taken by the soil or not? Now, if I go and calculate in the first scenario, okay, if I go and calculate in my first scenario, just 1 second. Okay. Now, for first scenario, how much is your stress? My stress is going to be 1,200 kilonewton. Okay, 1,200 kilonewton divided by, what is your area of the foundation here? Your area of the foundation is 3 into 4. Okay, 3 into 4. So that's 12, which will give me 100 kilonewton per meter square. So now what you are trying to tell me, you are trying to say for me that there is a pressure coming from the top, which is 100 kilonewton per meter square, and there is a safe bearing capacity. The soil can take up to 150 kilonewton per meter square. Now, do you think that the soil will fail in this scenario? Do you think that the soil will fail?
No.
No. Why? Because your loading is lesser than the capacity of the soil. Okay, your loading is lesser than the capacity of the soil. Are we clear about it? Okay. Now what about case number 2? Case number 2 is 2,200. My area as well is 12. Now, if we go and calculate, you will see that 2,200 divided by 12 will give you 183. Let's say 183.3 kilonewton per meter square. So I'm saying that there will be 183.3 kilonewton per meter square pressure, and then on the soil can take up to 150 kilonewton per meter square. Okay. Now what will happen in second scenario? What will happen in the second scenario? You will see that your loading is more than the capacity of the soil, so the soil will fail. Do you agree for scenario number 2? It will fail, right? The pressure is more than the capacity of the soil. Okay. How would you solve this issue? How would I solve the issue?
Increase the area.
Okay. So if you increase the area, what will happen? You will see that your stress is going to be lesser. Okay. Your stress is going to be lesser. Like for example, now your area, for example, I'm going to suggest that it's going to be 3 into 5 meters. Okay. 3 into 5 meters square, for example. So now my stress is going to be 2,200 divided by 15. So we will go and check 2,200 divided by 15. You will see that it's 146.67. Now, is it fine? 146 can be taken by the soil. Yes. Okay. So in this scenario, you are going to make sure that your foundation is safe. So one of the most important checks when it comes to foundation design is checking the ground pressure. Okay, one of the most important things you need to check for is ground pressure. Now we have mentioned already we are going to check for bending, we are going to check for one-way shear, we are going to check for two-way shear, but the most important thing that you need to check whatever we call it ground pressure. Okay, we need to check the ground pressure and check whether the soil can take it from the beginning or not. There is no point of me going to the bending or one-way shear and two-way shear, and the soil from the beginning cannot take this particular loading. Okay. So checking the ground pressure and the safe bearing capacity is one of the top and one of the most important checks that you need to do at the beginning of the foundation design. Are we clear about the pressure, safe bearing capacity, stresses? Are we fine about this? Okay, let us try to solve this problem, which is something similar to whatever has been solved with you from Miss Maison, but this is a little bit elaborated. So it says for you check the suitability to have an isolated or a combined footing for the encircled columns below, knowing that the safe bearing capacity of the soil is 150 kilonewton per not millimeter square. It is per meter square. Per meter square, and the width of the foundation is restricted to be 2.1 mm by 2.1 meter. Dead and live loads acting on the columns are of 1,300 kilonewton respectively each. So for each column, there is a dead load of 1,000, there is a live load of 300. Okay, and then they said for us that you are having a restriction of 2.1 meter. Okay, now if you see in these columns, now these are my columns. Oh, this is my column. Okay. Now, shall I put my foundation in this way? Or shall I put my foundation in this way? Scenario 1 or scenario 2? If scenario 1 y, if scenario 2 y. If scenario 1 y, if scenario 2 y. Now this is very important for you. The orientation of the foundation is very important. The orientation of the foundation is going to save you a lot of reinforcement if you are a good engineer. Now you can see here what will happen. Now if I have scenario number 1, you can see that I have this distance and this distance. I placed my shorter foundation. Okay, I placed my shorter side of the foundation with the shorter side of the column. And I have placed my longer side of the foundation with my longer side of the column to avoid huge length. Now in the opposite scenario, whatever you have done, you have placed your longer side of the column with a shorter direction. Now you will have a small length here, correct? But in the opposite direction, you are going to have a very huge length. A very huge length will cause you to have a very huge moment. Very huge moment is going to cause you to have a very huge reinforcement as well. Are we clear? Are we clear? Okay. Now, what I understood now, this is going to be the arrangement to be used. Okay. And you are telling me that the width is restricted, to 2.1 meter. Okay. Let's say that this is my width now, and this is going to be my 2.1 meter. Now I need to check the length of the foundation. I need to check the length of the foundation. Okay. I need to check the length of the foundation. Now, how would you check the length of the foundation? Can we get the area? Can we get the area of the foundation? Stress is equal to force divided by an area. How much is your area? Your area is going to be equal to force divided by stress. What is the maximum stress can be taken by the foundation? The maximum stress can be taken by the foundation is going to be your safe bearing capacity. Okay. Are you following up, or do you want me to solve this problem next class? Is it already too much for you? Because we are having only 4 minutes. Do you want me to solve it in the upcoming class? Okay. Okay, no harm. Okay. So already you have your force value, which is 1,300, and you have your safe bearing capacity, and accordingly you can calculate the area. The width is already given. Okay, the width is already given, and then you can calculate your length, and then from that you will check whether there is an overlap or not. So this is the basic concept to decide whether it's an isolated or a combined foundation. So nobody is going to come to you in real project and say for you that this is an isolated or a combined foundation. Okay, the problems when they will come, I mean, you will be having only the distance between one column to another column, and accordingly you need to decide whether it's going to be an isolated or a combined foundation, and then design it accordingly. Okay, so most of the books, most of the courses as well, if you go and see in the YouTube or the other colleges, you will see directly they are telling you that go and design a isolated foundation or design a combined foundation. But the most important thing before even designing an isolated and a combined foundation is to know when isolated is to be used and when combined is to be used. Okay, so before going to the isolated foundation design, first we should know how to classify or how to say, no, shouldn't be an isolated, this should be a combined. And accordingly, then the next step is to start designing it. Okay, doing that, we have finished today's session. If you have any question for today's session, you can ask. If you don't have any question, then you are free to leave. Once again, I would like to remind you of Sunday test, because I'm not going to meet you on Sunday. So I wish you all the best in the test as well. Okay. Any questions that you have? If no more questions, then we have finished today's